Okay, so welcome everyone. This is week 11 code walkthrough. Week 11 covered deep generative models, diffusion models. Subtopic covered in this week were Introduction to Diffusion Model, DDPMs, Classifier and Classifier Free Diffusion Guidance, Text Condition Diffusion Models, and Sampling Prediction Space, Noise Schedules, and Architectures in Diffusion Models. So, we'll wait for maybe 5 more minutes if anyone is planning to join, and then we'll start the session. Muting myself for now, uh, but wait for maybe 5 minutes and then we'll start. Okay, I'm muting myself for now. Okay, I think we can start the session now. No. So today we will be discussing the diffusion model. In this particular tutorial, we'll be taking a deeper look into denoising diffusion probabilistic models, also known as DDPMs, diffusion models, score-based generative models, or simply autoencoders, as researchers have been able to achieve remarkable results with them for unconditional or conditional image, audio, video generation. Popular examples include Glide, DALI 2, latent diffusion model, and ImageGen. We'll go over the original DDPM paper by Ho et al., which came out in 2020. Implementing it, we'll implement it by step based on the Phil Wang's implementation. Link is given here, which itself is based on the original TensorFlow implementation. Link is given. Note that the idea of diffusion for generative modeling was actually already introduced in 2015 in Seoul Dickstein paper. However, it took until Song et al. Uh, 2019 at Sanford and Ho et al. In 2020 to independently improve the approach. So, ideally or realistically, this is not a new approach. This approach has been there since 2015, but it took some time to uh, improve the model and get it to the up to the or better, make it better than your generative adversarial networks. So it became better in 2019 2020, independently by two different researchers at Google Brain and Stanford. So note that there are several perspectives on diffusion models. You can check this link. Here we employ the discrete time latent variable model perspective, but you can also check the other perspective. So this is the 2020 paper. We started all of this denoising diffusion probabilistic models. If you want to go or read this paper, you can read. It's okay. So we start with the some import statements. We'll be creating our diffusion model in PyTorch. So first of all, what is a diffusion model? A denoising diffusion model it's actually very simple idea. If you compare it to other generative models such as normalizing flows, GANs, or variational autoencoders. So in all these models, you convert noise from a simple distribution to a data sample. And this is also the case where a neural network learns to gradually denoise the data from pure noise. So in a bit more detail, we set up our setup of diffusion model consists of two processes: a fixed forward diffusion process of our choosing. That so we basically we choose a process Q and gradually adds Gaussian noise to an image until you end up with the pure noise. That is, we start from a image, we gradually add noise, add noise, and finally at xt step, x capital T step, we are at the isotropic Gaussian noise. Okay, and we also learn a reverse denoising diffusion process p theta, which we call p theta, where a neural network is trained to gradually denoise an image starting from pure noise until you end up with the actual image. So now you're starting with the noise, you're denoising a very small step at a time, you're denoising, and finally getting your original image. So now both the forward and reverse process are indexed by t, happens for some number of finite step capital T. So in DDPM paper, this paper, authors use t equals to 1000. You start with t equals to 0, where you have a real image x naught from your data distribution. You may or may not have access to that distribution, and the forward process. So forward process samples some noise from Gaussian distribution at each time step t, which is added to the image in the previous time step. And given a sufficiently large capital T and a well-behaved schedule for adding noise at each time step, you end up with what is called a isotropic Gaussian distribution, which is a pure noise. In more mathematical form, you can write this down more formally, as ultimately we need a tractable loss function which our neural network needs to optimize. So let q of x naught be the real data distribution, say of real images. We can sample from distribution x naught. So suppose you got a real image, say this face image, from some underlying distribution. We define a forward distribution process as a conditional distribution given a conditional distribution over xt given xt minus 1, which adds Gaussian noise at each time step t according to a non-variant schedule. So we know at which time step how much variance should be there in our data or in our image. So based on that, we are simply adding the noise based on that schedule, and the conditional distribution for any arbitrary time step t uh, given xt minus 1 is given by this, where root 1 minus beta t times xt minus 1 is your mean and beta t times I is your variance. So recall that a normal distribution is defined by two parameters, mean mu and variance sigma square. So this becomes our mean. One second. Okay. This becomes our mean and beta ti becomes our variance. So what which we can do by sampling from epsilon. If you have already done variational autoencoders, you must be aware of reparameterization trick. So what you can do is you can sample from a standard normal distribution, and then you can add whatever. If you want to change the mean to say root square root of 1 minus beta t times xt, you add that term. And if you want to change the variance to beta t, you multiply the square root of that with epsilon sample, which is a sample from standard normal distribution. So note that beta t are not constant at each time step t. In fact, one defines a so-called variance schedule, which can be linear, quadratic, cosine, which we'll see further. So starting from x naught, we end up with x1, x2, xt, x capital T, where x capital T is pure Gaussian noise if we set the schedule appropriately. So basically, we are starting with something, and finally, we want to reach at the say this the mean of our distribution should become zero, so that way we can set the value of beta t. Okay. So now we know the conditional distribution of xt minus 1 given xt. Then we could run the process in reverse. So if we know the process, then we can run the process in reverse, but by sampling some random Gaussian noise at x and then gradually denoising, we'll end up with a sample from real distribution x naught. However, we don't know this probability distribution of xt minus 1 given xt. It is intractable since it requires the knowing the distribution of all possible images in order to calculate this conditional probability. Hence, we are going to leverage a neural network. So we'll be training a neural network to denoise. Given a noisy image, can we go back one step? Can we go one step back to get a denoised image? Okay. So we'll be using the neural network to approximate this, and we will call this p. It will be parameterized by theta, so we can call it p sub xt minus 1 given xt, with theta being the parameter of neural network and operated by gradient descent. So, okay, we need a neural network to represent the probability distribution of backward process. If we assume this reverse process, it's also Gaussian, then we can recall that any Gaussian distribution is defined by parameter mu theta and sigma theta. So instead of learning directly learning the final values of images, what we can do is we can learn the parameters of this distribution from our neural network. Hence, our neural network needs to learn, represent the mean and variance. However, the DDPM authors decided to keep the variance fixed. So, in the reverse process, this DDPM paper authors keep the variance fixed and let the neural network learn the mean of this conditional distribution. Okay, so first we set the mean to be sigma square I to untamed time dependent constant, and sigma t square as beta t and sigma t square as beta tilde t to get the similar results. Okay, this was later improved in improved diffusion models paper, where a neural network also learns the variance of this backward process besides the mean. Okay. So we continue assuming that a neural network only needs to learn represent the mean of this conditional probability distribution. So now we'll define a objective function by reparameterizing the mean. To derive the objective function to learn the mean of the backward process, authors observe that the combination of q and p theta can be seen as a variational autoencoder. Hence, a variational auto lower bound can be, if you are aware of this, you know that when we do variational inference, we basically use this variational lower bound, which we use to minimize the negative log likelihood. Instead of directly minimizing likelihood, we'll use this lower bound with respect to ground truth data x theta. It turns out that elbow for this process is nothing but the sum of the losses at all the time steps. By construction of forward Q processes and backward processes, except for L0, for loss is actually the KL divergence between the two Gaussian distributions, which can be explicitly written as a L2 loss with respect to the means. So a direct consequence of our constructed forward process Q, as shown in the paper, we can sample xt at any arbitrary noise level conditioned on x0, and we don't need to apply Q repeatedly in order to sample xt. So basically this just means that you don't have to go from x naught to x 100 one step at a time. You can define a schedule like this. You can define a schedule like this, and basically then you can derive a noisy image at any time step using this schedule. Okay, so yeah, this is just the algorithm which I have explained just now. You start with x naught, you sample your input image, then you sample t. Basically you sample t, which means the time step at any time step. Then you get your epsilon, which is the sample from standard normal distribution, and then you calculate the mean square error loss between the noisy image and the denoised image, which you can sample from at any step using the schedule, and then you take the gradient with respect to the parameters to update the parameters. So overall, we take a random sample x naught from real no unknown density data distribution. We sample a noise level t uniformly between t1 and t, which is a random time step. We sample some noise from Gaussian distribution and corrupt the input by this noise at level t using the noise property reparameterization trick. And this property which I had defined just now, which is defined in the paper also. And then neural network is trained to predict this noise based on the corrupted image, that is noise applied on x naught based on a known schedule beta t. In reality, all of this is done on batches of data as one uses stochastic gradient descent to optimize neural network. So for a neural network, we need to use a autoencoder because we want to start with the input image and end up with a same size image. So for this particular case, we use a unit type architecture. So neural network needs to take a noised image as an input and returns a predicted noise. So note that the predicted noise is a tensor that is same size and resolution as input image. So technically network takes in and output tensors of same shape. What type of neural network we can use? It's mostly we'll use an autoencoder for this purpose. In this particular paper, they use DDP UNet architecture or UNet model for this. So as we can know, for a simple brief overview of UNet model first downsamples the input, makes the input smaller in terms of spatial resolution, after which it performs upsampling. Okay, so we'll define some helper functions. These are some simple helper functions. Positional encoding, I think we have already discussed. This is just to define your UNet model. So till now we have, suppose I'm not gonna go through your UNet model architecture in this particular tutorial. So suppose you have a unit model. Now we define the forward diffusion process. The forward diffusion process gradually adds noise to an image from the real distribution in a number of time steps t. This happens according to a variance schedule. The original DDPM authors employed a linear schedule. We set the forward process variances to constant increase linearly from 10 raised to the power minus 4 to zero point 0.02. However, it turns out that another paper which came out in 2021 improved diffusion process that better result can be achieved if you use a cosine schedule. So we define a beta cosine schedule, linear schedule. Cosine schedule means basically we'll follow a cosine wave to update our parameters, which is our variance. Linear, quadratic, sigmoid. To start, let's use the linear schedule t equals to 200 times step 200 times step. Define the various variables from beta t which we will need, such as the cumulative product of variances alpha bar t. Each of the variable below are just one dimensional tensor. We just need to store the values of alpha bar t, not the whole thing, not the noised or denoised image. Okay, importantly, we can also define an extract function which allows us to extract the appropriate t index for a batches of indexes. So we define that schedule here. Uh, Assume we have this particular image. we want to add the noise to this particular image, say at the certain number, a certain time step. So we will basically, what we will do is we'll simply say that okay, I want the noisy image at this particular time step. What this function will do is it will calculate the mean and the variance, corresponding mean and variance for those at that particular time step, and just give return the image at that time step based on our schedule. Okay. So our diffusion process is very simple. We just take our alpha bar and then pass this alpha bar to our extract function, which takes in the input image x0 and adds a no, basically returns a noisy image at that particular time step. So we can test that image at a certain time step, say time step 40. You can see that it has added a large amount of noise at this particular time step, and you can play around with this number, like say t equals to 0, what will happen, and t equals to 1, what happens. And you can, if you try to see that, you will be able to see that this is adding the noise very slowly. So let me run this whole thing first and then show you. Give me 1 second. So if I show you say 10, or let's start with 1. Let it run. You can see here that get noisy image is doing nothing but getting a sample from noisy and doing reverse transform. Reverse transform is nothing but simply some transformation which we had done on the data. We just want to do the reverse transform, like converting to tensor, or in changing the channel from first to channel last, or dividing it by 255 or 250, like that 255 normalization. Also you can see here at the first time step it adds some noise. Now if we go at 10, so you can see it adds more noise, but it is less than the noise at say time step 20 or 40. Time step 40 it is very noisy, and if we increase the time steps to say 100, this becomes like almost noisy, but it's still, we can figure out that there's a cat in this particular image. But if we go for say 200, not 200, 200 is our last time step, indexing starts from 0, say 199, you can't figure out anything. This becomes like full isotropic Gaussian, sample from isotropic Gaussian. Okay, so now we can visualize different time steps. I have shown you already. 0, 50, 100, 150, and 199 time steps looks like this. We can define the loss, like we have a X noisy, we have our neural network or our unit model which predicts the noisy image, and we want to get the, we can have a L1 loss, that is mean square error loss between the X noisy and predicted noisy, or L1 loss means your one norm loss, just the difference, absolute value of the difference. L2 loss is MSC, mean square error loss, and then you have a Huber loss, which is a smooth version of L1 loss. So we do this, and then we define a PyTorch data set and data loader. So we have to define a regular PyTorch data set. The data set simply consists of images from a real data set, like a fashion MNIST or CIFAR 10. We resize each image to same size. It is interesting to note that the images are randomly horizontally flipped from the paper. We are using whatever has been done in the paper. So we run this, we load the data. Okay. So now, as we will sample from the model during the training, we define the code for that. This is the same code. Generating new images from a diffusion model happens by reversing the diffusion process. So reverse diffusion process is we start from the last time step, which is capital T, where we sample pure noise from a Gaussian distribution and then use a network to gradually denoise until we end up with time zero. As shown above, we can derive slightly less denoised image by plugging in the reparameterization of mean and using our noise predictor. Remember that variance is known ahead of time. DDPM paper, variance is actually fixed. We are not learning the variance. So ideally, we end up with an image that looks like it came from the real data distribution. So here we define that p sample function, and this is just a p sample loop. We train the model. So let's say we define our model, which is unit, then our architect, our optimizer Adam. In our forward, in we do it for number of epochs. We do the training for number of epochs. Each epoch, we go through all the images in our data loader. We calculate the loss by using our p losses function. P losses function. One second. P losses. This is our p losses function, right? I have already described that. And if we do this, we can see how the model is training and how the loss is decreasing. It is simply a mean square error loss or absolute error loss. So we can see the loss is decreasing, converging or decreasing fast. It goes from 0.48 to 0.128. So we are going to run for say 5 epochs, still in the first epoch. It's no 1, 2, 3, 4. It is currently printing a loss at every 100 steps. So let's see how many times it will print. Maybe it will take some 2, 3 minutes to run. Let's wait for it to finish running. So the loss is decreased, but now the decrease in loss has reduced. So you can see that now it is little bit fluctuating also 0.0605, 0.0605, like that. Uh, let's see. Yeah. Can stop this now. I think whatever this has run is enough. So let's see if we want to sample from the this particular model, what will happen. See, uh so you can see that because I stopped early, right? You can see that there's some shape we are getting, not very good, but some shape we are getting, and you can change the random index to say 1. You will get something, say 10. You will get something, right? So yeah, so overall this was your diffusion model. uh, I hope I was able to explain it to you properly. If you have any questions for this, you can ask in discourse. And yeah, yeah, I can wait maybe for 5-10 minutes here, and if anyone has any question or planning to join, they can join. Thanks for being listening to this tutorial. I'm muting myself. If anyone will join, I will unmute myself. Okay, so I don't think anyone is planning to join, so I will stop the recording now. and stop the live streaming. I will be here for another maybe 5-10 minutes. If anyone is joining, we can start the recording again. Stop the recording.